Page 3 of Complex Numbers and Polynomials for HL Chapter 6. Write 1 plus I quantity to the fourth in simplest form, hence find 1 plus I to the 101st in simplest form. Let's see, take the 1 plus I to the fourth. This could be written as a binomial expansion. So you could put 1, 4, 6, 4, 1. And the first term won't generate anything useful here, so you just ignore that, right? Because 1 times 1 times 1 times 1 is just 1. Now the I, we're going to write that the first term is going to have I to the 0, second term I to the first, third term I to the squared, I cubed, and I to the fourth. I squared, of course, is -1. I is just I. I to the 0 is 1, just like everything else to the 0. I cubed is -I. And I to the fourth is like -1 times -1, which is 1 again. So this is, and look, this cancels with this, right? So we're left with 1 minus 6 plus 1, which would be -4. Okay, that's interesting. So if I do 1 plus I times itself 4 times, I end up with -4. So if I multiply 1 plus I to the 100th, that would be equal to 1 plus I to the fourth to the 25th, right? So that would be equal to -4 to the 25th. Okay, so -4 to the 25th, interesting. And now it says, hence find 1 plus I to the 101st in simplest form. So that would be equal to 1 plus I to the 100th power times 1 plus I. So that would be -4 to the 25th power times 1 plus -4 to the 25th power times I. So we could, look, even if you took the negative times itself 25 times, you just get a negative, right? So this would be -4 to the 25th, 1 plus I, like that. I'm not sure if it's worth doing 4 to the 25th. That's just, a huge number. I think we can just leave it like that. So when I checked in the book, the way they wrote this was instead of 4 to the 25th, they converted this to 2 squared to the 25th, which is equal to 2 to the 50th. So they wrote it like this, 2 to the 50th times 1 plus I instead, okay? But I don't see anything special about this except for the fact that a lot of times the powers of 2 are more famous than the powers of 4, but the power of 2 to the 50th is not a famous power of 2, so. Okay, number 6. Suppose z equals 2 minus I and w equals 1 plus 3i. Write in exact form a plus bi. Okay, so z divided by w, that would be 2 minus I divided by 1 plus 3i. So the way I do division is I just make adjustments to the fraction so that I don't have any part of the complex number in the bottom. I don't have imaginary parts in the bottom. And the way I do that is I multiply by the complex conjugate, right? So on the bottom, I'm going to have 1 squared. The outside and inside terms cancel out. And then -3 times 3 gives me -9. I squared gives me -1. So it's 1 squared plus 3 squared, which ends up being 10, right? And on top, I'm going to have 2 for the first terms multiplied together. Negative 3i times negative I would be positive 3i squared, which would be negative 3. That's the last term. And then the inside terms would be minus I minus 6i. And so it would be 2 minus 3 is negative 1. Negative I minus 6i is negative 7i. And then the bottom will have 1 squared plus 3 squared, which is 10. So that's pretty much it. We could rewrite this as negative 1/10 or negative 0.1 minus 7/10 or minus 0.7 I. Okay. And let's see. W divided by IZ. W is 1 plus 3i. And divided by Z is 2 minus I. Times I. Okay, because I times Z. I just switched the order here. Hope that doesn't confuse anybody. So I'm going to simplify a little bit by distributing the I. So it would be 2I and then minus I squared, which would be minus negative 1, which would be 1. So that's simplified. Now I'm going to multiply by the complex conjugate, 1 minus 2i, in order to perform the division. Okay, so the bottom is going to be, it'll be 1 squared, negative 4 times negative 1, which is 4. And then the top is going to be, first term is 1 squared. And the last term is going to be negative 2 times 3, which is negative 6. I squared is negative 1, 6. And 3i minus 2i. 3i minus 2i. Okay? Okay, and 7 plus I divided by 5. And that is equal to 7/5 plus I divided by 5. Okay? All right, number 7. So we have I divided by 1 minus 2i. So this is a division once again. So in order to do division, I just multiply the complex conjugate of the denominator so that the bottom has no imaginary part. So it'll be 1, negative 2 times 2 is negative 4, times minus 1 is positive 4. And the top is going to be I, 2 times negative 1 is negative 2. So negative 2 plus I over 5. Negative 2 plus I, and each one is over 5. C, we're doing a subtraction between two imaginary or complex numbers with complex numbers in the denominator. Not a coincidence that the denominators are complex conjugates to make life easier for us. So to add together fractions or subtract fractions, remember that you want to multiply by a factor so that you make the denominator common between the two. So for the first one, I'm going to multiply both the top and the bottom by 2 plus I. The second one, I'm going to multiply both the top and the bottom by 2 minus I. And by doing that, the denominator becomes 4. Negative I times I is negative negative 1, so it's plus 1. So the denominator becomes 5. And the numerator, let's do the numerator. So 1 times 2 plus 1 is 2, or 1 plus 2 plus I is 2 plus I, minus 2 times 2 minus I divided by 5 equals 2 plus I, negative 4 plus 2I. So 2 plus I, negative 4 plus 2I. Okay, divide by 5. And so I'm going to combine like terms. So negative 2 plus 3I, and each of those terms is divided by 5. Number 8, so if z is equal to this and w equals to this, find the imaginary part of 4z minus 3w. Okay, so 4z would be 4 times 2 plus I minus 3w, so 3 times negative 1 plus 2I. And we're going to find the imaginary part of that later, okay? So let's distribute the 4. 4 times 2 is 8 plus 4I. Negative 3 times negative 1 is plus 3. Negative 3 times 2I is negative 6I. 8 plus 3 is 11. 4 minus 6 is negative 2I. And let's see. What is the imaginary part of 11 minus 2I? It would be negative 2I, right? One thing I kind of noticed I was doing wrong is when they use this imaginary notation thing. So if they say the imaginary part of 11 minus 2I and the imaginary part is negative 2I, they only want you to give the real part of the imaginary number, not negative 2I. They just want you to say negative 2, okay? All right, that's kind of weird. Okay, let's do the next one. Imaginary part of iz squared. So first I'm going to have iz squared, which is I times 2 plus I times 2 plus I. That's equal to I 4 plus 4I plus I squared, which is negative 1. So it's equal to 3I minus 4, right? Because I times I is negative 1. Negative 1 times 4 is negative 4. Is that it? Yeah. So actually, I'm just going to reverse the order. Negative 4 plus 3I. And then I'm going to take the imaginary part of that. So the imaginary part of negative 4 plus 3I is equal to 3. On the page 178 reading, talking about equality of complex numbers, if you say that two complex numbers are equal to each other, that is equivalent to saying that the real parts are equal and that the imaginary parts are equal. Okay, moving on. Find the exact real numbers x and y such that, okay, so let's do A first. So let's take a look at that. So let's equate the real parts and the imaginary parts like this rule says, okay? So 2x is the real part and negative x is the real part of that one. So let's equate those. So 2x equals negative x. Now let's equate the imaginary parts. So plus 3yi, we could put I2, but they'll just cancel out, equals negative 6i. Now that we made them equal to each other, we can cancel out the i's. And here, let's see, if we add x to both sides, we'll get 3x equals 0. So we then know that x equals 0. And here, 3y equals negative 6, so we divide both sides by 3, and we get y equals negative 2. All right. C. We're going to do FOIL to the left side because we want to put it in the form a plus bi. So we're going to put 2x plus 2yi minus ix minus I equals 8 plus I. So let's simplify the left side. So let's mark the real part, so 2x, and maybe that one there. So 2x, and I squared is equal to -1, so this would be plus y, so that's the real part. And then the imaginary part would be 2yi minus ix. So we'll write 2y minus xi, and that is equal to 8 plus I. So now we know that 2x plus y equals 8, and we know that 2y minus x equals 1, right? Because here's 8 and here's 1. So now we have a system of linear equations. Let's do substitution. So we'll do y equals 8 minus 2x. We'll put it into there. So it's 2 times 8 minus 2x minus x equals 1. 16 minus 4x minus x equals 1. 16 minus 5x equals 1. 15 equals 5x. X equals 3. Let's check that answer. It's okay. So let's put this back in. So we'll have y equals 8 minus 2 times 3. 8 minus 6 equals 2. So y equals 2.